Welcome to Chapter 2, Atoms and Elements. When we're talking about elements here, we are not talking about these elements: earth, air, water, fire. Everything changed when the Fire Nation attacked. Not those kind of elements, although that is a really great show, and if you have not seen Avatar: The Last Airbender, it's actually even fun for adults. It's not just a kids show. But that's not what we're talking about here. We are talking about these elements, the elements from the periodic table. We're going to learn about very briefly anyway, about the history of chemistry. And by very briefly, I do truly mean very briefly. There is a lot of history behind the study of chemistry. We're just going to barely skim the surface. Then we're going to get into the atomic theory, talking about what atoms are made of, what different elements are made of in terms of the numbers of those subatomic particles and things like that. So we're going to get into that in this chapter here. To start off with, we need to define some of our terms. So element, our definition for this is going to be a substance that cannot be broken down into simpler substances. Now, elements can actually be broken down into smaller particles, but those particles are subatomic particles, and so we are not going to call those substances. Similarly here, atom, we're going to define this as the smallest unit of an element. So it's the smallest piece or the smallest bit of that element that we can get. So this here is one way that we try to visualize an atom. As we'll see later on in this class, this is actually not a great way of representing an atom, but it's better than nothing. It's good for showing to kids in grade school and things like that, to kind of give them an idea of what an atom is like, but atoms actually don't really look like that at all. So, a little bit of history here. Since the 5th century, people have theorized that all matter is made up of small, indivisible particles. Essentially, the idea was that if you got, the tiniest little knife and you just kept cutting a piece of something into smaller and smaller and smaller pieces, eventually you would reach a point where you couldn't cut it into a smaller piece. There was some elementary particle that things were made of. And this was all the way back in the 5th century when this was theorized. So over the years since then, many scientists have put forth theories on similar subjects. So there was the law of conservation of mass, which we will get into a little bit. The law of definite proportions, the law of multiple proportions. We won't get into those two quite as much. But the best known theory about what constitutes atoms, what atoms are made of, was what's known as the atomic theory, that was put forward by a scientist named Dalton in the early 19th century. So this was the early 1800s. His theory had 4 basic parts to it, and those were: number 1, each element is composed of tiny, indestructible particles called atoms. And this is mostly true. Like I said a minute ago, you actually can take an atom and make it into smaller particles, but we don't consider those particles to be elements. Those are subatomic particles. They're not very stable on their own. They're really only stable in an atom. Number 2, all atoms of a given element have the same mass and other properties that distinguish them from atoms of other elements. And this is again mostly true, but as we'll see later in this chapter, it's not 100% true, because you can actually have 2 different atoms of the same element that are not exactly the same in every way. They can have different masses, as we'll see later on. But for the most part, this is very true. There's just some exceptions. Number 3, atoms combine in simple whole number ratios to form compounds. This one, 100% true. No exceptions. You are never going to find a molecule out there in existence that is made up of 2 oxygens, 1 hydrogen, and 3/4 of a chlorine. Like it can't happen. It's physically impossible. So compounds where you have atoms coming together, they're always formed by whole number ratios. You're never going to get fractions of an atom. And then number 4, atoms of one element cannot change into atoms of another element. In a chemical reaction, atoms only change the way that they are bound together with other atoms. And this is, again, almost completely true. There are actually exceptions to this, and these would be the radioactive elements. There are some elements that are inherently unstable, and they break down over time. They turn into other elements because of that instability. So with that exception, then everything else, for everything else, this is true. So the only situation where this is not true are those radioactive elements. But for everything else, this is true. So all things considered, Dalton's atomic theory was actually really, really good. For the time that it was made, the time that it was created, again, the early 1800s, where they were very limited in their scientific tools, it was really mostly just theorizing. This was incredibly good for the time. Like I've pointed out, it was not perfect, but it was really, really good for the data and the instrumentation they had at the time. As time progressed, people started to realize that things were not quite as simple as they thought they were originally. They started to discover particles that were smaller than atoms. So this is around the same time that Dalton was forming his atomic theory. A different scientist named J.J. Thomson actually discovered what he called cathode rays. This is what we now call electrons. So he had this cathode ray tube, is what he called it, set up, that was partially evacuated, and he would put a really high voltage across the tube, and what he would see was particles shooting across from one side of the tube to the other. And those particles actually reacted to magnets. You could bend the stream of the particles with magnets. And so this was the discovery of the electron. This was essentially the first neon light, although it is quite different from what we would consider neon light nowadays. In principle, it is very similar. So Thomson was able to find the charge to mass ratio of the electrons by manipulating the cathode rays, as he called them, in an electrical and magnetic field. But it wasn't until a different scientist named Millikan did an experiment with some oil drops, very, very, very tiny oil drops, that the charge of the electron was determined. So, because we knew the charge to mass ratio from Thomson, and because Millikan was able to figure out what the charge of an electron was, combining those two together, they were able to determine what the mass of an electron was, and it is really, really tiny. Very tiny. 9.1 times 10 to the negative 28 grams. Impossibly small. You cannot imagine how small that is. So, with this information, J.J. Thomson, the guy that discovered the cathode rays in the first place, proposed a theory for the structure of atoms. And this is what we call nowadays the Plum pudding model. And what J.J. Thomson theorized was, we know that we have these atoms, and I have discovered this particle that is smaller than the atoms, that is inside the atoms, that has a negative charge. And so he theorized that atoms were made of this positively charged goopy stuff, and that the electrons were little negatively charged particles that were dispersed within the positive goop. And this was the best theory that they had for a while. It was taught in schools for a little while. But a different scientist named Rutherford decided to test this theory. And the way he tested it was using what we call now the gold foil experiment. He had a radioactive source here that was shooting alpha particles. And alpha particles are a lot bigger than electrons, but they are still smaller than atoms. Technically speaking, they are actually the nucleus of a helium atom, but they are smaller than atoms. And so they are shooting out of this source here, going really fast, and they come into contact with a very, very thin piece of gold foil. Now, it looks decently thick here, but he was using very thin gold foil for this experiment. Think like gold leaf thin gold foil. And so what he was expecting was that when he shot these alpha particles at the atoms, because the Plum pudding model says that the atom is mostly just this positively charged goopy stuff, because the alpha particles are so tiny and so high energy, they should just go straight through. They should just zip right through there. They're bigger than the electrons, so the electrons can't stop them. And they're going fast enough that the goopy stuff can't, it might slow them down some, but it won't cause them to deflect or anything. And so that's what he was expecting, was to see all of the alpha particles go straight through to the other side and impact the detector over here. And what he saw was that, in fact, most of them did. Most of the alpha particles did go straight through the gold foil and impact this detector on the opposite side. But quite a few of them didn't go straight through. Some of them deflected a little bit, which you could possibly say is just, maybe the electrons can't stop them, but maybe they can kind of pull on them a little bit and push them a little bit, and so that wasn't terribly unexpected. But then there were quite a few that deflected a lot, that deflected way off to the side, or even backwards towards the detector. And the Plum pudding model has nothing in it that can explain this. There's nothing in the Plum pudding model that could not only significantly change the direction of an alpha particle, but have the alpha particle go backwards, impact it and go backwards. There's nothing in the Plum pudding model that could explain that. And so Rutherford proposed a new model for the atom. He said that the atom is not made of a whole bunch of goopy stuff, like we see here. Instead, what if the atom is mostly empty space? That would explain for most of the alpha particles going straight through. But there's a small portion of the atom where you have very densely packed matter. So you have a very dense region of the atom, and if the alpha particles hit that, then they would bounce off of it because it's so dense. So this is what he called the nuclear theory. So Rutherford's nuclear theory, we're going to go through the three main parts here, just like we did with the atomic theory. He proposed a theory that said, part 1, most of the atom's mass and all of its positive charge are contained in a small core called a nucleus. That is 100% true. Every atom has a nucleus, and that is where practically all of the mass in the atom is. Number 2, most of the volume of the atom is empty. It's empty space through which tiny negatively charged electrons are dispersed. Also 100% true. Number 3, there are as many negatively charged electrons outside the nucleus as there are positively charged particles, which we call protons, within the nucleus, so that the atom is electrically neutral. Again, 100% true. So, Rutherford's theory is really, really good. However, even though all three of these points here, you might have noticed, unlike the atomic theory, I said all of these are 100% true, it's not complete. So he was correct in all of these, but he still didn't have the whole picture. It wasn't until later that one of Rutherford's students, a guy named James Chadwick, demonstrated that there was this unaccounted for mass in the nucleus. There was mass that should be there and it's showing up, but they didn't have any way of accounting for the mass. They had extra mass, essentially. And so he proposed that there were neutrally charged particles in the nucleus, that are called neutrons. So now we have our complete list of subatomic particles. Protons, which are positively charged. Neutrons, which have no charge, but have the same mass, roughly. For our purposes, we're going to say they're the same. Mass as a proton. And then electrons, which are negatively charged and much smaller than either the proton or the neutron. So we're going to pick up here in the next video.